Hello everybody! In a series of videos, I'm planning to provide you some skills in using ANSYS, which is one of the most common and popular software in finite element method, or in other words called FEM. The lessons are from zero, and it means that there should not be any prerequisite except for being a mechanical engineer for sure. I will try to teach you all I know, and at the end you will know what I know. It is worth to note that the ANSYS provides two different interfaces. One is called Workbench and the other is APDL, and both use the same solution core inside. Here we are working in APDL because it is more easy to learn the basics and we can skip the complexity of a sophisticated GUI. Also, it is much easier for us to use coding in APDL. Well, we start with understanding firstly what the finite element method is. I will try to make a very simple example of an element, then try to generalize the idea to a system of components. Then we talk about why geometry is important for us and what is the FE model. Then I will give you some examples of different elements which are the components of an FE model. Next would be an introduction to the ANSYS APDL environment. We get to know where is where, and in the end, we will compare the FE results with analytical results to see how much FE analysis would be effective in solving our problem. So let's firstly start to understand how we solve physical problems. Various phenomena treated in science and engineering are often described in terms of differential equations formulated by using their continuum mechanics models. Solving differential equations under various conditions such as boundary or initial conditions leads to the understanding of the phenomena and can predict the future of the phenomena. Exact solutions for differential equations, however, are generally difficult to obtain. You may remember hundreds of formulations used for analytical solution, but you may also remember they are limited to some simple geometries and boundary conditions and loadings. On the other hand, numerical methods are adopted to obtain approximate solutions for differential equations. Among these numerical methods, those which approximate continua with infinite degree of freedom by a discrete body with finite degree of freedom are called discrete analysis. Well, FEM is the method using the same approach in order to give you an approximate solution, and it is very helpful. For sure, having an approximate result is better than having no results. Although in many cases you will see this approximate scale is tiny enough to be neglected. Well, the third approach is the one used thousands of years, and it is experimental methods. In this method, the sample or the prototype is tested under equivalent loadings. The experiment planning and design is a very vast field and can be very complicated plus expensive also. Well, in a high-tech industry, although engineers use all three methods in order to make sure they are designing in the edge, but the FE analysis can reduce the design process highly. Well, let's begin with understanding how finite element works. Here we have a steel rod. On both ends we may introduce displacement or force. Then we would like to know what would happen to this poor rod. Let's see what do we have from before. From equilibrium, we already know that the force on the left side is equal with the other direction comparing to the other one. This is a static analysis and it is not a dynamic analysis. We don't have any acceleration, so we already know this. And from elasticity, we can connect the force with the displacement of this rod with these formulations. This is a very simple problem, and uh, all you may give the answer with analytical solution very quickly. But we are going to make a system which this rod is one element of that system, and for sure we need a systematic solution. Let's proceed with our simplification. I just decided to change the direction of this force, and I put minus here, and I rewrite the equation like this, and for force 2 I just write the formulations. Now I have two equations, and by solving this system of equation, I will understand the behavior of my system. But it is more easy for me to translate this system of equation into one matrix equation, and it has two benefits. First of all, it is more organized. You can see the force vector and the displacement vector. And second, the matrix equation is very easy for machine to be worked with. Let's take a look at the items inside this matrix in between. Here we have the model of elasticity, and A is the cross-section of our rod, and L is the length of our rod. So this matrix comprises the geometrical and material properties of my components. And if I rewrite my equation like this, I can understand that the force is connected with the displacement with a kind of matrix which which describes the uh, geometrical and material properties of my component. And this equation may recall you something in your mind. If you can remember the Hooke's law, the spring and the force, you may remember that we connect the force applied to the spring with the displacement by these formulations. And here the K is the spring constant, and it was connected to the material and the geometrical properties of the spring. And here we have the same thing. It is very similar. We have force, we have displacement, and we have this matrix in between. And we call this matrix a stiffness matrix because if we reduce the values of these components of matrix, the stiffness of the system will be reduced. And if we increase the values of this matrix, we have more stiff system. So we managed to make one simple equation for our problem by replacing it with just a line and 2 points. Actually, this line with the two corresponding points has a name. It is called element, and the 2 points are called nodes. In this example, every node has just 1 degree of freedom. They can just move from side to side. Now let's see how elements help us in solving complex problems. Let's make our life a little more difficult and add some rods together. Now we apply the same formulation for every rod. And we write the matrix equation for rod A, for rod B, and also for C. Then how we can assemble all these three matrix equations together and have one matrix equation? That would be rather easy. You may notice that the matrix to be generated is a 4 by 4 matrix. We just move every item in the position they should be, and when we have two items in the same place, we just sum them up. And now we have the same rows and the 4 columns that we wanted. Now we have an assembled matrix out of all individual ones we had. We call this new matrix global stiffness matrix, and we call it global because it connects the the displacements, all the displacements of the system to the force vector of our system. And let's review what just happened. We had a system of components and we just translated it into some lines and nodes. And at the end, we extracted one matrix equations. And you may notice that if the number of these elements are increased, the size of this matrix is increased. So the number of elements in those are related to the size of the matrix equation that is going to be solved. And it will affect the calculation time of our machine. Well, it is important now to understand that the geometry is different from FE model. In fact, the geometry is used just to provide us the elements, and at the end we just deal with the elements and nodes. Sometimes even we don't have any geometry in our analysis and we directly import the FE model to our analysis. The process of making elements out of geometry is called meshing. If the size of the elements are small comparing to the geometry scales, we call it fine mesh, and if it is large, we call it coarse mesh. Well, there are different types of elements. You may see here the solid elements, which is a very popular one. This is the first order solid elements because we have nodes at the edge of the elements, and it can be in different topologies. Here we have the hexahedron topology, and for example, here we have the tetrahedron one. This is the plane elements. These elements are used to solve the plane stress or plane strains problems, and you may notice that the nodes of this element has just 2 degrees of freedom. There are 2D elements, 2D elements, and they cannot move in, for example, Z direction. They just can move in 2 directions. And also it can be used in triangular shape. This is the shell elements. It is of kind 3D elements because every node of this element is able to move in 3 directions. Also, every node can rotate in the 3 directions also. So every node of this element has 6 degrees of freedom. Also, this is the beam element. The beam elements can be in first order or second order elements. And there are lots of other element types you may use in different cases. Well, one component can be simulated with different types of elements, and it is up to you, up to your decision that which element type should be used. For sure, you should consider time of the calculations and also the accuracy of the results, and you should always consult your engineering vision for that. A good decision may lead to a better results. For example, here we have the same geometry which is meshed with 2 different elements. On the left side, you can see the tetrahedron elements, and on the right side is the hexahedron elements. But you may consider that the results may be different using these 2 types of elements. First order tetrahedron And also, triangular elements should be avoided as much as possible in stress analysis problems because the elements are overly stiff and exhibit a slow convergence with mesh refinement. If they are required, an extremely fine mesh may be needed to obtain results of sufficient accuracy. About the mesh refinement, we will talk in the examples at the end of this video. Now we can see here the first order and the second order elements. On the left, you can see the first order uh, tetrahedron element, and you can see what will happen after the formation of the element. Here you can have an image of the element, how it is shaped. Maybe it is difficult to understand what is the shape of the element here, but you can imagine from this shape. Before deformation, this is the what is called, I can say that it is light blue. The node after deformation is displaced to this point, and this node to this point, and this node here, and this node here. So after deformation, you have this shape of the element. On the other hand, you see the second order element, by which you may better describe the system deformation. In the second order elements, you have these mid-span nodes. You can see that this element is more flexible to accept the deformation. So maybe with this element, you may describe your system much better. Well, for solving an FE analysis, you have to go through different steps. Firstly, you have the geometry, which includes key points, lines, areas, or volume. And with the help of material properties, you generate the elements and nodes. And then you apply the boundary condition loadings over the elements. Now your model is ready and it is solved. Then you have the post-processing step. And the first result that you may obtain from structural analysis is always displacement. And from displacement, we can obtain strain and stress. Now let's take a look at the ANSYS environment. Here is the ANSYS APDL environment. In the top here, you may see the utility menu. In utility menu, you can find file, which with this menu, you can do different things like changing directory, resuming your file, and importing different files, exporting files, and etc. From select, you can select different components or different items and entities. In the list, you can list different things like lines, areas, volumes, even you can list properties, the loadings, and also the coordinate systems. In plots, you can plot different parts of your model. You can plot elements, nodes, lines, whatever you want. And in plot control, you can change the options how your plots can be seen. In work plane, you can change the coordinate system, for example, from Cartesian to cylindrical, or even you can define a new local coordinate system. In parameters, you can find the scalar and array parameters, and also you can define new ones. In macro, you can develop and apply codes to your analysis. And in menu control, you can change the options of the menus that you have. And in help, you can consult help. Here is the main menu of APDL. In this main menu, you have different libraries of functions, and with these different functions, you can generate your model, you can solve it, and you can see the results. And here is the input bar. With the input bar, you can insert comments. And instead of using the GUI, you can directly write your comments in order to use different functions. And this is the toolbar. These are some shortcuts for different functions. And this is the graphical window. The graphical window is where you can see everything. And there is another window, which is this one. This is the output window. You can see some logs in the output windows. Okay, let's come back here uh, in these different steps of the finite element analysis. We can categorize different steps into some categories of steps. We can put these model preparation into pre-process. In the pre-process, we apply material properties and geometries in order to make the elements, and we can apply boundary condition over it. And then we have the solution step. In the solution step, you solve your model. And also in this step, also it is possible to apply boundary conditional loading. And in the post-process step, you may see the results. And in the ANSYS environment, you can see all these three steps. You can see the preprocessor where you prepare your FE model, and here you have the solution where you can solve your model, and then you have post-process parts that you can see the results. Now, let's solve a very simple analysis to understand how finite element works. Here we have a cantilever beam, which is on one side fixed, and on the other side we apply a force which has a distance from the blade tip. The material of the beam is steel with the modulo of elasticity of this value, and the Poisson ratio is 0.3. So we are going to apply beam elements and also solid elements to this example. And with this example, we already know, we already have the analytical solution. And if we apply these measures and these values to these formulations, you may obtain the analytical deflection. And I already have done this calculation and obtained the deflection of 0.92 millimeter for this beam. Firstly, I will try to model this beam with just one line, and I will apply the beam element over this line and get the results, and then I will try to model this problem with solid elements. I will use both second order and first order elements for the solid elements that we may apply to this example, and see what would be the difference between all these three elements. Well, let's start with ANSYS APDL. First of all, you should consider that I'm not going to tell every detail. It is just for fun, and we want to understand how the results of the FEM is compared to analytical results. So do not worry about the details. First of all, I'm going to prepare my model. First of all, I will try to define the element type. I will go to the beam element of first order. Then I will try to define the material properties. It is linear isotropic material with the module of elasticity 2.1, E11, which is 210 gigapascal, and the Poisson ratio is 0.3. Well, and now I have to define the section of the beam element. I use the common sections and yeah, the rectangular one, and it is 5 millimeter to 10 millimeter. So I just put 5 millimeter here and 10 millimeter here for the section. Now I have to make the geometry. For the geometry, I just have line, but before making the line, I have to make some key points. First, in the coordinates, I will apply that. Don't worry about these things. Um, you will learn in next videos how you can work with all of these. So do not worry if you cannot follow. And actually, you are not supposed to follow. You just sit back and relax and enjoy. We have two key points here, and I will define the line between these two key points. It's my line here. Yes. Now I'm going to mesh this line with beam elements. And because I'm going to apply force 10 millimeter away from the tip of the line, I will select the size of my element equal to 10 millimeter. So I will change the size of the yes, my element to 10 millimeter, and I mesh my line. Okay, and if I take a look at the nodes here, you can see the nodes of the elements. And for the elements, you cannot see elements very good here. If I change the color of the elements, you may see them much better. Yes. Yeah. You can see here that we have 9 elements for the model. And if we apply the cross section over every element, you may see the beam that we are working on. Yes, what is option? Yeah, this is our beam. Yeah. So I'm going to fix this end and apply load here. Okay, let's go back to the line illustration of the elements. Yes, here loading. I just apply a displacement constraint over this key point here. I just fix this point. I will fix all the degree of freedom for this point because it is a fixed constraint. And then I will apply force over this node here. And it is in y direction. And because it is in the opposite direction of the coordinate system, I will apply minus here. And now you can see that we have a beam which is constrained in one side, and we apply it load in the other side. Now let's solve our model. Okay, it's very easy and fast solved. And let's see the results. Yeah, if I show you, yeah, here it is. You can see that the beam has been deflected, and the maximum deflection is 0.92, which is very close to the analytical results that we obtained. Now we are going to apply the solid elements to our model. Well, I don't want to waste your time. I have already done it, so we just see what would be the results. Yes. With the first order solid elements, uh, we could reach somehow the result, but the accuracy of the result is not satisfying me. And let's see how many elements has been used for this analysis. It is 288 number of elements that is used for this analysis, and the solution time is 0.35 seconds. Let's see the elements. You can see that this number of elements is used for defining the model, and these are the nodes. There are a lot comparing to the beam element, but the result is not satisfying, so I'm going to increase the number of elements to see if it helps or not. So I just change the index of the meshing and make the element numbers double. Yes, with increasing the number of elements by 2 times, I'm getting close to the results. You may remember that the analytical result was 0.92. It is close to that number, but it is not satisfying me. So I just increased the number of the elements. But before that, let's take a look at the number of elements. The number of elements uses 2,300 number, and the solution time is 0.93 seconds. And if I show you the elements, you can see that how many elements is used, and the nose is much more comparing to before. And if I increase the number of elements, let's make it double. You just felt that this solution was taking higher time comparing to previous one, but the result is satisfying here. We have reached the analytical results, and let's take a look at the numbers. The number of elements that is used is 18,000, and the solution time is 5 seconds. So we just found out that the solid elements is not good for solving this problem. But what if we change the element type from first order to second order elements? Let's see what will happen, and I will just change back the number of the elements to the lowest number, and I will apply the second order solid element. Let's see what will happen. Yes, you can see that we reached the results of the analytical solution with the same number of 288 elements of solid first order that we didn't reach the results. So by changing the elements type from first order to second order, we got a much better results. And if I tabulate all the results, you may find out that for the first order solid element, we tried firstly with 288 elements, and the calculation time was 42.42 seconds, and we didn't reach the satisfying results. We increased the number of the elements, and we reached to the satisfying result when we had 18,000 elements, and the time is dramatically increased. But with the second order solid element, we had with the lowest number of elements, we could get the satisfying result with a reasonable time. But the best result was for just 9 beam elements, and the timing for solving these 9 elements is quite low, and we reach very good results. So again, you just notice that you may solve your problem with different types of elements, but the things that is important that it may takes a lot of time in order to reach the result with the wrong selection of the elements. And if you choose the right element, you will reach the results in a faster way and more accurate. Thanks for watching, and see you next time.